Okay, let's start the third review class. And you can see hello again. Okay, I just hope that I will at least use seeing the video. So, yeah. We have seen again, I wanted to review again the part of the Fermi-Dirac generate gas, because it's quite important to understand that due to the packing, compressing the gas, we raise the density, and this rise in density reduces the space for each particle. So we localize more and more the particle, and this will show the quantic effect to the particles, and we start to see the effect of the degeneracy. That, just to remember, the distribution with the highest degeneracy actually could be are the other, the Maxwell-Boltzmann and the Bose-Einstein. That because the degeneracy is when you have multiple states with the same energy level. So you have a degeneracy in the energy. But if you have infinite degeneracy, that means you have no limits, so don't see a lot of the problem. The opposite is when the degeneracy is low, like in Fermi-Dirac, that you have this fix for just two, you just can be one set for each particle of quantistic number. And the other are more correlated with the energy, it means just the spin. So you have just two fermions for each energy level. Then it will limit the way you can put strictly the way you can put the particles. So when you are really packed, the energy and the momentum start to increase, and then you cannot have the same value for everyone, and so started to feeling more and more the highest energy states and energy level with the higher energy. And you see all these aspects that were essentially things usually it's in the temperature, the side, the distribution. In this case, since you are limited on the number of states, it's the distribution of the states that cause an increase on the mean momentum, and so as we saw, the momentum connected with the pressure, and the pressure obey to the density that causes the momentum instead of the temperature. Now we'll see again. We already saw in the first lesson, so a little more quicker about the radiation. We have energy that flows from higher concentration to lower diffusion, classical. If you need to have a flow, usually have a gradient, a diffusion. crazy. Thermodynamics. Then you increase the disorder, the entropy, so flow from higher to lower. So you have from higher temperature to lower temperature, so this means that the luminosity must be equal to the minus a gradient, or at least proportional. This is the classical. You have intensity of some energy entering, or intensity of some properties entering in a small slab of material, and for interaction goes continue a little less than before. We have E entering and E minus the E, the I and the I exiting this part of material. And it's one model that difference is proportional to the intensity in itself. If the increase also the difference. And you can see if you put below the I means that essentially the rational proportional variation is constant. And the other is proportional to K, it is opacity, the density, and the size of this part. It means also the opacity by density must be 1 over a length. So we consider this product 1 divided by K, the density characteristic of the free mean path. Of the particle we are considering, photons essentially, then this product K rho and the distance, depth on the material is called optical depth. The called tau can be like here with the plus or sometimes with the minus. Depends. It changes a little. Someone put the minus to have an exponential to tau, other keep this positive just to have a minus tau. That means that increasing the optical depth, the intensity will decrease. And this is also how we define the photosphere. That is when the optical depth among us and the photosphere is should was defined by Eddington, the famous Eddington. And the temperature at the photosphere is called the effective temperature of a star. The opacity depends on usually on the density, temperature, and the frequency of the radiation considered. And in general, you can see that so there can be interaction among the photons and the material, causing a loss in the intensity, and can be due from several effects, starting from the center, seeing what before the effects are working more in the center of a star, so higher density, higher temperature. The first is essentially Thomson scattering or electroscattering, that is just an interaction among a photon, an electron, and a scatter. In this case, there is no exchange of energy, just change in direction. And you can see that the opacity in this case doesn't change with the frequency. It's perfectly equal at all the frequencies. When you start to have a really high temperature, 1 billion of Kelvin, we start to have it's really high energy. So we have high energy photons and really high energy electrons. So we start to have a relativistic version that is the quantum scattering. There, the photon changes energy. Another is free absorption. That means that a photon interacts with an electron, but in this case there is also they are nearby of the ion, and using the ion, the photon in this case is just absorbed by the electron that increases energy, and this what is opposite of Bremsstrahlung. Bremsstrahlung will be this breaking emission, where an electron passing in nearby of an ion due to the Coulomb field turn, emit a photon and use energy. In this case, it's the opposite. It's just like Bremsstrahlung in reverse. Outer part, we can have FF is free, B is upper bound. I put here the reference, and is referred to the state of the electron. Here the electron was free before and free after. The other can be the bound free, the electron is bound to an atom and then it is free, so ionization. And can depend on the outer part, there is all can be all the element. In the inner part, just the element with really high Z, really high atomic number. Obviously, there is also the opposite inverse reaction, the free bound, that is relative recombination. So the photon, some atom can be ionized, some can be recombined, so emitted the photon. Obviously, in that part is most probably ionization, but actually it's in equilibrium. B in B outer part is a photoexcitation. This is usually definitely in the outer part of the stars, less than 3000 Kelvin, so outer border of the envelope of the giant, supergiant star, or in the above part of the star, with the absorption and the inverse procession, that is the emission. The spontaneously induced by collision. Sometimes you can have a photoexcitation you can have excitation also by collision. The collision can excite an electron, it can be goes down emitting, or an electron can be excited and by collision going to emit. And this is, you see, definitely a lower, that's just on the really more cool stars outside. Then there are the extreme case on the outside with the bound by free by an atom of hydrogen with two electrons, not one, but it's an ion, negative ion of hydrogen, and bound of molecules, dust, in this case are. So all this part in real outside of the red giant, super red giant stars. really cool. You need a really low temperature and the effect. Delta E also depend on the famous Einstein coefficient, spontaneous emission, induced emission, absorption. Is increased with the two emission, spontaneous and induced, and decrease with the absorption. Together, essentially, what we consider are the opacity given mostly by band bound, band free, and free free, and the scattering. It is apart. This is because it has this part can have to be corrected by induced emission, while the scattering, electroscattering, has no this problem because it just changes direction. It's not can be spontaneous or induced. You can define the opacity in this complicated way because you need to mean average on all the case, and essentially instead of using k, you use the inverse of k, k, kappa. This is not a k, this is a kappa, and Greek letter. So you have 1 over kappa mean over the intensity divided by the intensity to have this mean value called the Rosseland mean opacity, because it was proposed by Rosseland. This is a good way to study mean on all the interval you are considering. Usually here infinite means from the center of the star up to now, to us, to us, because there is a small effect actually also in the between. You can just consider inside the star. Yes. This intensity is based on what we observe. You can approximate everything with the famous Kramer law, that just given the opacity with a constant value and the power of density and temperature. Scattering, as Scattering said, doesn't depend on anything, just as constant, and on the molecular mass correlated with electrons. That we remember is more or less this one. This is approximation, I remember, because it's obtained thinking that the mass number of the element is always twice the atomic number. That is not exactly true, but for in this case, it's a really good approximation. Doesn't change. It's not a problem. In other moment, in other cases, you have to do the right count. And you see the value is small, it's not so strong. Then we have free, the absorption to the inverse Brownian. You need all this to mean over composition with a classical this rho with the power of 1 and t to the 3.5. It is essentially the value used more for the Kramer law. Usually, when you're talking about Kramer opacity, you mean with this exponent. And you can see the depend on this one. The constant is definitely bigger. Can vary. Also vary by the density and the temperature. They decrease. If you're really high temperature, this will decrease. And so we consider that temperature around 1,000,000 is for free, that is 20. Anyway, this stay at the order of 100, 1,000, definitely bigger than this one. And obviously depend on the molecular weight, since we are is interaction with electron. Bound free, it's again depend on various factor, similar Kramer opacity, and in either higher. So this ionization can cause really high opacity. In fact, usually the highest opacity is in the envelope of the star, not essentially inside. And you see this is max among 3, 5, 10 to the 1,000 Kelvin, where is the hydrogen and helium ionization that we saw yesterday in the art. Not so far away, well, that is the statue ionization. So we can see the Riemann path of the photon at this value. We can calculate characteristic value. Usually inside the star we can put 1 gram. Mean value, the opacity around this value. And you see that is 1 centimeter. This is a small value, essentially, of the scatter. As you saw, this can be higher. So this is putting this value, you have an upper limit for the mean free path. And you can see here that the gradient along the mean free path, it's this value. Yeah. And then a photon see a gradient temperature just of 10 to the minus 3 Kelvin. So definitely small. It can be for the radiation, the grand, we can see like the temperature is constant. Okay. This that is the mean free path, not free mean path as I wrote before, above. It's the mean, the average of the free path. That means the more or less the path, the length that the photon cover between two interaction with the matter. That means that a photon inside the star that can travel just 1 centimeter before interacting with something. This is also the reason why it takes so long for the energy produced inside the star to go outside, because it's continuously interacting with something, absorbing, emitting, and also explain why the energy inside the stars is produced a mega electron volt, while outside we see the electron volt or less. Then we, for this reason, in the framing part, the gradient is really small, so we consider constant, so we consider local moment equilibrium, so we consider that in every shell the intensity is connected with the black body, but the body means that it is isotropic, so there should be no flux, and we have flux. That's because this is really smaller than 1, but it's not 0, so you have almost, but not exactly. You have you can see the approximation with the black body is really the same, except for a really, really small amount, and that small amount permit start to radiate. This is typical of physics when you have something that until viscosity can be really small, but not 0, and that causes everything. So you can see that the radiation is almost like the body, good approximation, and that small difference permit emission. So we have some part, the radiation, and going through some other part. Here we have higher energy, temperature, and pressure. We're going to some part with less energy, less temperature, and less pressure. We can see in the two ways. The energy of an electron is P by C. Also, an electron is connected momentum. And so we saw before that in a relativistic particle, like a photon, the energy is connected with the momentum multiplied by C, the momentum multiplied by the velocity. But actually, is the same because velocity is C. So, but in classical, there should be divided by 2. But here it is not. The divided by 2 enter because in relativistic there is the gamma, there is the square root, and with approximation the square root become a multiplication of 1/2. Remember Taylor series approximation. So we have the difference of intensity can be expressed in this way. That you can go down and you get to the luminosity is equal to the flux, and intensity of the flux multiplied by the surface, so for P Greek R square, and you get this result. Here is the E goes in this direction, and here we substitute the E with the previous definition in this way. It's just changing the momentum with its value with the related to the pressure. This is K is a constant. There are essentially this. So at the end we have this result. Similarly, we can see here the diffusion, the flux of diffusion is constant by the variation of the density in 1/3. The velocity diffusion and neutrino path, velocity C, neutrino path is kappa rho, and this value goes to the radiation internal energy, and you got this value. Okay, this is similar, but that proportion. At the end, what we have is this nice relation that gives us the luminosity of the radiation. It's this part that is not complicated to remember, because you just remember it's okay 4p square, because it depends on the radius. And since we are talking, it's connected with the radiation. Center came from the pressure, radiation pressure, that is 1/3 to the 4 A, then enter, then is inverse proportional to the proportional to the mean free path, so opacity density is below. Then okay, you have the C that came from we can just check for the that all the physical properties maintain the units. Checking with the units, luminosity is energy by time, and just in this way, usually it's better than remembering everything perfectly, or just with some deduction you can obtain this. Here is in the Eulerian and Lagrangian notation. And then there is the opposite, that are the gradient of temperature in function of luminosity, opacity, and temperature. This is important because you have this is the gradient that supports this L. So if you have this gradient, you have this luminosity, but also this is the gradient that is needed to transport a certain luminosity. So if you have a certain luminosity, you have this certain gradient of temperature. Because remember, the variation of energy is equal to the luminosity, nuclear luminosity, that is integral on the energy source, nuclear source or energy source actually inside the stars, minus the luminosity of that. Energy produced less than the luminosity lost from the surface, or at least a certain level of internal of the stars. If you have an equilibrium, these two must be equal. So you have to consider it from inside to outside, increasing the radius, the luminosity must always be equal to the energy produced inside that sphere. And this luminosity are pushing to have a certain gradient, at least mean, because the gradient can change for some reason, you see, but at the end, if you see on the surface in the star, you know the internal temperature, the external temperature, the luminosity is fixed like this. You have at least a mean value. This luminosity. As we saw after, this is luminosity, essentially radiation, but more energy transportation by radiation. You see a little better later. There is a convection that when this gradient determined by luminosity start to be too high, more than the adiabatic, it starts the convection, and we have this value 1/2 because half goes up and half goes down. The heat capacity, constant pressure, density, the velocity of the material, the typical length of the material, and this is the gradient in pressure, or can be multiplied by the difference of this logarithmic gradient adiabatic less the actual in the matter is the material. Since this is negative, this means that this has to be negative, so we start when this value is greater than the adiabatic. Then we have transportation by neutrinos. They are a really long mean free path, so they just go away, just losing. So if you consider the neutrino luminosity from nuclear reaction is just subtracted by epsilon, so it's already considered. The neutrino luminosity from other process is just a meter loss and are calculated as a negative luminosity. In the last, when there is really high density, you can have that actually the mean free path of the neutrino could be comparable with the radius of the stars. So you need a formulation for the interaction among neutrinos and matter. It is quite complicated. This is also why it's not so easy to model the last phases of the star life, especially the moment of supernova, because there is the situation is quite problematic. We have extreme version of the physics. Another is the conduction. Usually the framing path of the electron and ion are really smaller than the framing path or mean free path of the photon, so usually is definitely negligible the flux. Here this is flux, L is the luminosity. This is energy by second by surface. L is just energy, is the power, energy by time. The usually definitely smaller the radiation, it starts to be just when the generate gas D. That in this case, and we saw usually the momentum is connected with the Fermi energy, that when there is high degeneracy, it's bigger than the thermal energy. So you have that the star and then the generate matter is moving really faster with usual. Then that this permits to have here the momentum connected to the degeneracy higher than momentum connected with the target. That means that this has to be really higher, so bigger, and be really effective. You can process equally because you have this situation. The conduction flux is anyway proportional to a gradient of the temperature because it's due to a gradient difference in temperature. So we can write the formula for the conductive flux similar to the radiative, and then we put it together and we can sum the two opacity, the real to the radiation and what is called the opacity from conduction together to have just one. Nuclear reaction. Here we go again. Oh, let's see. As I said, nuclear reaction is what gives energy to the star. We can say that the mean energy production per unit mass in a star, that can be simply as the total luminosity external, what you see outside, divided the total mass, really small, just 2 erg by grams by second. And this is because obviously we are not using nuclear reaction are not in all of the stars, just in the core. So the real mean value, because okay, this can mean because the L epsilon can vary with the temperature inside the stars. So we can just, this is the mean value, this is for all the stars, this is just for the core. And see the total luminosity divided the mass of the core. And what is this value? C. Then actually it's the mass of the core, but not only mass of the core, or multiplied by the mass fraction, the element we are considering in fusion, because only cannot use all the core for the real value here for the produce energy. So this depends also on the here essentially from the sequence is multiplied by the fraction action of the hydrogen. For nuclear particle, we have boson, fermions, and we saw boson is with the integer spin, and fermion with the half integer spin. Boson are photons, meson, alpha particle, in general on the atomic nuclei with even mass number. Fermions are electron, proton, neutron, and atomic nuclei with an odd number of mass number, odd value. Then this depending on the spin, the other depending on the weight are the hadrons and the lepton. Lepton are the smaller, the light, not connected with the strong nuclear interaction. Lepton are usually more common known are the electron and the neutrinos. Hadrons are more massive. The name hadron means massive, electron light. Are made by quark. Baryons are 3 quark and meson 2 quark. Also, we have several types of rays. Alpha rays are ionized nuclei of helium-4. Beta rays are electron, and gamma rays are photon, usually at the energy of megaelectron volt. This is what is more commonly named gamma rays. Sometimes we use gamma for all the kind of all the photons, not only the really high energy. Type of nuclear reaction are fusion, spallation. Fusion, okay. Fusion of two, you have two particles, they stick together and form one another one. Or maybe emit a small electron. spallation, your nuclei hit by a particle is the heat is energetic enough to break the atom in take away, essentially, not break the nuclei, the nucleus, but take away some parts, small fragments. This is usually what causes production from lithium, beryllium, and boron. Induced gamma emission, like induced photon emission, but in this case we have the nucleons in the nuclei that emit decay in the state and emit gamma. By photon or absorb. Alpha decay emit alpha particle. Fission is very heavy nuclei are absorbed and light particle and split into parts. It's big way of the spallation. Spallation usually can be also light nucleus, like nuclei. Like fission usually are really high mass number, and they are breaking two parts usually equal. This part usually no spallation can just take away some part, some like the lithium take away some part and reduce slightly the atomic number. And beta decay that is due to the weak interaction. The nuclear reaction can be usually in this way. We have target particle and projectant particle collide on the target and will produce a main product and secondary product. Each one is mass number and atomic number. That can be also mean the mass number as the number of baryons, and Z like then the charge. All can be resumed in this way with X the target, usually the biggest, heaviest particle of the two. The projection, comma, the secondary product, and the main product. Remember that all the reaction always must be at several conservation law. It is the angular momentum, spin included. So spin is an angular momentum, intrinsic, but is an angular momentum. So the sum of the spin among the reacting particle must be equal to the spin of the product particle. The charge, contain the charge, rest mass energy. So the energy here can be equal to the energy here. The baryonic number and the leptonic number. The number of lepton here must be equal to the number of baryon, and lepton here is equal on the other side. An antiparticle has a negative number and a particle has a positive number. Obviously, for example, a proton have a baryonic number of 1 and lepton number 0. An electron has a 0 as baryonic number and 1 as electronic. A positron, that is an anti-electron, has a -1 as electronic number. Then you can have also other conservation of number. The strangeness, charm, bottomness, and topness, they are connected with this quark, the strange, the charm, the bottom, and top quark are peculiar, but it's not interesting in our case because we are just considering baryonic, the neutron, proton, and electron. Our case. The nucleation usually can be seen as shown before the production of two product and two reacting particle and products. But to understand better, usually is so in this process, the two reacting fuse in the excited intermediate atom, and then this atom will go here. Here, the channel depends only on the energy of this intermediate particle, angular momentum and parity, and none of the weight. Once this is produced, it doesn't matter how it's produced here. When you are here, the channel goes essentially in the characteristic of that node of the fathers. So if you go here fusing to proton or proton neutron and positron to get the same doesn't matter. Usually it's better seeing the other way. If you are fusing proton neutron, that is in the pairing, and see that what happened. Can be also like two proton and electron, with proton and electron fusing to create a neutron. But once you have this intermediate nucleus with that energy, with that momentum parity, that decide what are the several channels. Like you can be just the elastic scatter. And essentially the two particles are like using two marble, they hit each other and goes away. Or in elastic scatter, one or two particles maintain most of the energy. The particle emission, that is classical, you have a main product and secondary product. Relative capture, that you maintain the intermediate excited nucleus, and just decay emitting a photon. The name is strange because usually when you consider capture, you think that you're capturing the photon, but actually this is an emission. Maybe probably can be because can be produced just by capturing a photon and then emitting. Fission is when you have your several of your main product are not just one but several with some minor particle emission. It can be, for example, neutrons, like in the case of the uranium fission. And some condition, this is non-nucleus, doesn't make sense, but nucleus, the framing part of the nucleus must be smaller than the size or the radius of the nucleus. It must be stay inside during the reaction, and otherwise you have the scatter. If the mean free path is higher on the radius, meaning the particle will escape. And also the mean energy of the excited intermediate nucleus divided by all the nucleus, the number of all the nucleus will be less of the separation energy, the energy to break the nucleus. Yes, if you are giving too much energy, obviously the nucleus cannot be stable, it will break. So if the two conditions are not verified, usually you get this one, or at least the inelastic scatter. You cannot have the other, because you can, definitely you cannot have this case. Important is called the Q value, that is the sum of the rest mass of the reacting particle less the rest mass of the product particle. When this Q, you can see here how you can write it, and considering we also define this delta M, that is the max excess of the particle, as the its mass is different among is similar, in actually opposite. If you considering the difference among the mass of the particle and the sum of the mass of its nucleus. This is simplified actually, because you consider they all have the same mass. Essentially, the mass of nucleus is 1/3 of the mass of the C12 the carbon, an atom of carbon with 12 nucleons, 6 protons, 6 neutrons. Usually this is not, the neutron is slightly bigger than the proton, and but is to show if the particle has an excess of mass respected to its reactant. That also should mean that it is more stable. And what we have is that this is because also Q can be seen as the sum of the difference among the mass excess of the sum of the reacting less than the one from the product. Here is important, if Q is positive, that means that the reacting have more mass than the product. And then we are losing mass, that means we are some of the energy rest, that was in as a rest mass is transformed in another kind of energy, so we are producing. If Q is positive, you have an exothermic reaction, produce energy. If it's negative, you are endothermic reaction. Endothermic essentially because usually the reactions are thermonuclear, depend on the temperature. So Q value positive means you are releasing energy and you will increase the temperature of the matter, the gas you consider. Another important is the binding energy, that is similar. You're considering the difference among is slightly similar to the excess mass, that's changing the sign, but is more specific if you're just considering if your reaction, perfect reaction among, you have the stand of the nucleus start with all its nucleons separated, and you put all together to produce that nucleus. For example, if you have the binding energy for the helium, you are considering here 2 protons, 2 neutrons, and with their mass, actually real mass, here mass of proton, mass of neutron. Then you subtract the mass of the nucleus of helium, 4, and the difference in the rest mass is the energy that has saved. The reacting particle less product particle. If it's a positive, this means that putting together you losing energy. So this is energy going in the binding energy, binding system. It's also the energy you need to give to the nucleus to reverse the have the several nucleus separated. And you see here the Z. I brought in this way to define from the function for the metal. It is the numeric atomic number, that is charge, so the number of protons in the nucleus, so the number of protons only. Here, the number of neutrons is just the mass number less the atomic number, by definition. What is mainly used is not that directly this here, like the Q, but divided by A. So this binding energy per number of nucleons. If you plot, you see that I have this band. If you consider the binding energy is a constant, and you see this is in function of the mass number, this should be follow a behavior like this in a parabolic curve. You see that it's not hyperbolic, it is not going down as hyperbolic. But at least we see that it is going up, arrive at maximum nearby the family of iron, and then goes down. This means that to fusing the iron, you are to produce the iron, we produce energy, because there is a relation between the Q divided by A and the binding energy of the product. Essentially, if you consider a fusion, so the two reacting particles are the same, and we are just emitting a photon that brings the energy. The Q value, you can see, is just divided by number of nucleons, is the binding energy of the product less the binding energy of the reacting particle. In this case, 1 and 1. So here we have 56. Check. Going should be like middle. You fusing these two, it should be silicium, and you get the iron. This is the difference. That means that fusing it, you produce energy. But when you try to fuse the iron, its product is here, is less, so you take this less this one is negative. That means the Q value is negative, and it's not more exothermic but endothermic. B demanding I, binding energy by E, can be expressed in this way, in mega electron volt. Several parameters. Here A usually is 14. You see that here the value is 8, and you have this several part. This increase part that is given by this, that essentially here the difference is bigger because A is small, that when you increase A, that's the difference with the 14 started to decrease up to 8. This is given because there is what is called the surface tension effect. In when you are in helium nuclei, the 4 nucleus are okay. The 4 try to stay as far as possible away from them, so stay really near the surface. Then when increasing, the more time is try to stay on the surface. Then as it increase, you need to populate internally. There's no more space on the surface for everyone, so you start to have more interaction among them. So it's less stable. If you consider the relation among area and volume on a sphere, you can see it goes like 1 divided the radius. The radius is the volume divided to the 1/3, and the volume is proportional to the number of nucleons. So goes in this way. And you see here, as increase the tension effect is less effective, so it's a little easier to break it down. It goes down is due to the Coulombian function that starts since the surface tension is less, so then new proton stay inside, so they try to push away the other. That here is that means that with the increasing, this is less. This should increase with A, but you see here decrease with A. True, but remember that Z in this part is like 2 times A. No, is 1/2 of A. A is twice the Z. So this is proportional to essentially to A. Here, so you have A to the 2. Here is A to the 4/3, that is less than 2. So this is increasing with A actually. So it's that you see here. The other two is less important. But this is because then here this is interaction, neutron-proton interactions that is stronger than neutron-neutron, proton-proton. So when are the same number, the number of neutrons and number of proton, this goes down and goes up. Actually, you can put some Z and add Z and take away Z, so we have Z plus N is A minus 2Z. So as soon as A is next to the 2Z approximation, this doesn't increase. When there is the difference, you have less binding energy, so it's less stable. This is also mean that the iron is really stable nucleus. It's really difficult to break it down. Nuclearization rate, what is important is to calculate how much reaction we produce, and we have okay, the simplification you consider in the barycenter of the system, relative energy, you have the velocity of the 1, 2 particle, the mass of the first or the second particle, 1 and 2, considering X is 1, A is 2, and so you can simplify in this way. B here is barycenter, not B. This just here after the calculation. Ion generacy is really high density, and usually when you arrive at this density, the atom just break down in proton and neutron, no more. So it's difficult to have actual ion generation. As we can see, if you're considering the temperature of nuclear reaction, usually it goes from 10 to the 7, 10 to the 9 Kelvin. That means kinetic energy, thermal energy of 100 kiloelectron volt. Not so high. Here is to calculate the cross section that the rate of the reaction. You can see like the velocity among the particle multiplied by the cross section, that is a surface. Classically will be the area, the cross section of the target. The biggest the target, the easiest is to hit it. The smallest is less easy. Actually, for nuclear particle that has no physical size, real physical size, this is more how is difficult or not difficult to interact with the other. That it can be seen as how near to that to the particle and to throw. You have the X particle target there. You throw in A several distances, and what is the minimum separation for to manage to it to have a reaction. Classical here is the numerical density of the first particle, numerical density of the other, and depends on velocity. And the reaction is a number of interaction by volume and by time. You can see here is length multiplied by surface is the volume, multiplied by numerical density is a number. So here remain 1 divided by time, and here 1 divided by volume. Consistency with this number. And also you can see that is the sigma, the cross section is see the number of interaction divided by number of nucleus X divided by the time of interaction, and below the number of projectilum and the area. Yeah, considering and the time. That is said classically will be give us essentially the probability of the interaction and collision. They classically have a geometric value. Here is just more probabilistic value than other. Here the minus from min infinity to plus infinity is not on the density, real density, but on the D, V2, because they decide the number of states. For calculating this, we'll go with the Maxwell-Boltzmann statistics, because as I said, is not a real statistic distribution, but is the one that is the other are quite nearby. It is easiest to calculate. We can consider isotropic distribution. We put together inside everything. These two, each one with his one. Do the calculation because each one is a velocity, and we use this transformation. And we got at the end of this result. That is the two density that doesn't depend on velocity. The density of the particle doesn't depend. That's the number on the state. It is this is it. It is the total here was connected with the velocity. I know it's formula in physics can be quite sometimes confusing, but this is the number of the numerical density with the certain velocity. Here is the total numerical density of that particle. That is the particle on the velocity. You have this awful integral that can simplify as a mean of these two, because it's the mean of the velocity and the cross section among the distribution. And you can see here is a v that is the relative velocity among the two that are of more important. The mean life of the particle X or particle can be seen as the numerical density of the particle divided by the rate that you can see here, because it's R essentially is the numerical density divided by time. So divided by the numerical density, you get just time. And you have to remember, and then put later put here, that is true when are different. If you are the same particle, 1 and 2, you are divided by 1. You can see here. At the end, the epsilon, the energy produced by per second per unit mass, can see just like the R that we want. Q this is not simple to calculate. This is easiest because we see just to weight and the product and the reacting particle, and then you can have it. You put inside, and you have the values. And here, in fact, this delta, the delta Dirac, that is 1 when A and Z are equal, and 0 on the other if they are not equal. This is because if you have the same particle, one particle cannot interact with itself. So here you have less. You have not consider one particle on the other, but you have to consider the pair. And if you remember the famous number, calculated the number of the pair with n particle is n plus 1 divided by 2. What happens? If you consider classically a nuclear reaction, you have a particle that will interact with the potential, the potential Colombian potential. We know that internally among this is the radius of the nucleus. Actually, inside there is the strong nuclear force that take together the nucleus. So there is a well, but to enter you have to surpass. It's like a wall. So if there is not enough energy, classically cannot enter. Because you can see the usually the level here of the barrier is a value of mega electron volt, but as we saw here, the typical energy, kinetic energy, is 1/10 of the mega electron volt, so it's not enough. Currently, a particle cannot enter a nucleus, so you cannot have mainly. And the tail of a maximum distribution is not enough populated to produce enough energy. In fact, it was at the beginning was thought it was impossible that the sun will produce energy with a nuclear reaction. It was just should be something else that was gravitational contraction, burning of material, carburant, something like that. Fission could be also, but not possible because this is the problem. This U value of the particle A, the projectile, we can consider X steel, we consider steel, is on the order of kiloelectron volt, while this value here is megaelectron volt. And also another things. This can be like the classical rail for the ball. To have a ball to arrive here, you need that here have a lot of energy, goes up, enter, but the problem, usually the ball, whoop, it goes out. Because, okay, at this size, you cannot think there is a friction. So if I have enough energy to arrive here, if enough energy to go out, so you cannot have a fusion. If there is not energy to go here, cannot enter, so you cannot have fusion. So classically, it's not impossible. For this reason, will help the quantics. We consider for potential well essentially two cases. One with the all potential wells, and there is all inside, or is a wall potential. More than the potential well, that is the potential well, is a potential wall. The potential well that classically the particle goes up, enter, increases local energy, and then whoop, goes up. Perfectly. Don't stop there. If you see instead in the artistic level, you will see that there is a small problem that here the particle will scatter behind, and another small problem that here will scatter behind. So there is the problem that the particle also in the highest energy can enter the well, stay inside a little, and then continue. Or you can see in the here you can see the red is the probability to be there, the particle. So outside the wall, the particle there is a constant probability because it can be here, move. But when hit any, this probability not goes down as classically. If you throw a ball to the wall, it cannot enter. It just goes down and expansion. So if you consider as before, the particle potential here is classically its probability to enter is 0, stop here, rebounds. But for quantity effect, is probability goes down. So at the end, when I arrive to the radius of the nuclei, there is a small probability. Yeah, in red is this probability, in blue the potential, that the particle appear here with this energy that was the one outside. That is called the tunnel effect. It was found by Gamow. This is also explain several things. Also, why our switcher is working, because you have little of oxidation on this on the copper part, so you should not have possible to have a contact transmit the electron. On other are some more effect that can be possible with the tunnel effect. Make some section, then we can. Okay, we saw that. Try to write betterly in the section here is can be seen as the geometric part cross section that is given by the size of the particle essentially is a wave number. Then this is statistical factor for spin, the transmission connecting with the tunnel effect, T transmission, L because also connected with the momentum. This part that is a resonance factor we see later, then symmetric factor, and what is the branching ratio that depends on the channel, because depending on what the result, the cross-section will be different, because the cross-section are for each reaction. That means that reacting particle, that product. The transmission can be expressed in this way: the width of the channel divided by the value. The resonance, we will see that are these other that depend on the resonant energy and the energy of the particle. So you can see that this value can vary. Generally, we can write the cross-section in this way. We explain as an exponential of eta multiplied by epsilon to the 1 alpha. That is because in this way is due to the transmission factor divided by the energy of the particle, and this SA that is change small with the energy, it is empirically calculated. You calculate as shown in class, usually when we are all experimentally, with the laboratory, empirically, we can calculate this S and plot and see, interpolate the value. At the end, we have that this mean is this huge that you can see here with the energy. Yes, these two parts. This has a shape of bell, where the max of this value, and for the temperature around, as usual, 10 to the 7 to the 9 is 510 kilometers volt. That is maximum, and it is exactly the value that we saw here, 100. So this shows why it's possible the nuclear reaction, because this is the maximum. That is what we call the Gamow window, that is the multiplication among the Maxwellian distribution, and the square E that is due to the tunnel effect. The multiplication among the two, you generate this value. Let's see here. Is not in proportion, the two actually. Just to show, you produce these windows where it's possible to have a lot more nuclear reaction. Okay, otherwise you should need, you see here it's 13 kiloelectron volt, here it's 15, 13 kiloelectron volt. To have actually, you should be classically here. It was not possible because to cannot stay inside. But tunnel effect permit to stay inside, to enter the quantities, to also to stay inside, and have this peak of production. like it. The total cross-section is this whole few things, where A here is the reduced mass number, and you can see when the Z I become higher, the potential, Coulomb potential can be higher. So also we have the that's easy, but also the velocity of the particle start to drop because the momentum is the velocity inversely proportional to the mass given the momentum. So you start to have lowest possibility of to have a reaction. So you need usually highest temperature to have highest reaction. The resonance is permit to create the to a little more stable. If the energy, you say that you have the two, you produce this internet nucleus in excited state. If this excited state is exactly one of the unbound energy level of the atom can stay a little longer until to decay and create a scatter. So this permits the reaction to be a little easier. And what happened is this one, as we saw before, the probability to the signal to the resonance in this way, because there is a constant here, and here the difference to the square. To this highest, you need to minimize this value, so you have to minimize this square, that is when the true energy is near, because to have this shape. So you have an increase of probability because you should less, and this will increase your probability to have this instead of a constant, to have that value that we call, for example, here when the resonance is quite nearby the gamma of window, you can have a really highest value for the reaction. Probably you have a peak here, then that will be stronger than nearby, so increase a little the temperature, and then the reaction start to run really fast. Another thing that is important, electron shielding. You have a lot of electrons, ions, so the two ions usually nuclear reaction is not that your particle projectile particle is an electron, are nucleus, so protons, neutral protons. If you have a lot of electron, because nearby of the ions, because attraction, this permits to reduce, and with certain condition, this reduction can be quite good. And when you have really high density, electron density, you can see is similar density, temperature, and similar to opacity, technically. And it goes up with the density. In highest density, you have this nuclear reaction. You have not thermonuclear, well, is due to the movement to the thermal velocity, but happen because the density is so high they are put together nearby. In a way that is can be similar, bring the degeneracy in the gas. And the particles are stick together really nearby. Each one is small space, so it's easiest to, in this case, to interact. There have less certainties in their position, so the certainty in momentum is highest, and it will increase their actual movement. Remember, the uncertainties are the difference among the mean, the value, the value of properties less is mean to the square cause the certainty. This is how we mean certainty. So, and certainty, highest certainty in momentum, that means that the difference among the momentum of the particle with the mean is high, or the technical value. It is the one given by that. So, piconuclear, you have this value for density. You can have 10 to the 6. You can have a piconuclear for the helium burning, 10 to the 9 gram per cubic centimeter for the helium, 10 to the 10 for the carbon. At the end, we can rewrite, you see, the epsilon can be reduced in this way, with the x is the fraction mass of the particle. These are the mass number of the particle. We are always considering nuclei to collide, not electron, for example. Let's multiply by the density in this one, and we can rewrite this one and see that we can write as a constant multiply by density to the lambda and temperature to the certain mu coefficient. And the sigma can be expressed in this, usually it's considered in this solution. Okay, I can continue, but since there is no one, I'll finish tomorrow with the nuclear reaction. Let's see, finishing to see nuclear reaction. We'll see briefly the stellar structure, polytropes, and then the stability. Quickly, because we have just one class, but this is what gives us, no one said nothing about what is of interest or what they don't understand. So I'm just showing, essentially. It seems more that it is a class for the public, so everyone wants to hear them. See you tomorrow. If you're wondering, I will be probably available around 6:30 tomorrow. That's the next class. This will be in half an hour. And no one enter, no one asked to ask. Come on. See you tomorrow and meeting.